Hello everyone, welcome back. So, in the last class we derived the modified partial differential equation which are the solution, exact solution of the numerical scheme that we are using. Okay. Now, we have a choice of numerical schemes, right. We have been discussing about many different schemes, okay, and we have some rough understanding of like which schemes work, which schemes do not work. Okay. For example, we have seen that the forward in time and central in space does not work for a convection scheme. On the other hand, that scheme is works pretty well for the diffusion scheme, for the diffusion problem, right. Further, we saw that if you use FTBS for a positive convection speed, you get a solution, but as you increase the grid size, the solutions become better. Initially, the solution is diffused compared to the condition that you have given, despite of the fact that you are not putting any diffusion in your problem, right. So, there are some numerical diffusion that is coming up, and that we saw in our modified PDE also, that despite of the fact that we are solving a PDE which is a convection equation, we are getting a convection diffusion equation, right. So, that is what is called the numerical diffusion. So, if you have a equation, okay, which is let us say del u by del t plus c del u by del x equal to 0, okay, and if you use a scheme which is let us say FTBS, okay, you are end up solving equation which is del u by del t plus c del u by del x is equal to alpha del to u by del x square, right. So, you wanted to solve a convection equation, but you are solving actually a convection diffusion equation, okay, and this term alpha, which I believe was something like c delta t by 2 1 minus c delta t by delta x, okay. So, this is basically coming purely due to the numerics, and this is called the numerical diffusion, okay. All the schemes that you are going to use in your CFD will have some or other amount of numerical diffusion. If there is absolutely no numerical diffusion, it is likely that your solution will blow up, okay. But then at the same time you want to make sure that the diffusion is not too much, right. If the diffusion is too much, then you are basically smearing out your profile. So, let us say if you have a shock like this that you want to resolve, okay, and if you have a scheme has got lot of diffusion, then what will happen, you will end up resolving a shock like this. You will get a solution, but it is too much smeared out, okay, too much diffused. So, we want to CFD as much as it is science, it is also an art to basically how to ensure that your diffusion is just enough to basically get you the correct solution. It should not blow up and it should give you the accurate solution that you want, that we want, okay. So, we have plethora of schemes, okay, apart from just like FTCS, FTBS or FTFS and so on and so forth. We have schemes which are basically the implicit schemes that we have discussed, okay, where you consider that my solution at n minus n plus 1 time is basically taken for the calculation of derivative at n plus 1 time, okay. So, that is also another scheme, implicit scheme, and we saw that for certain problems the implicit schemes basically gives you results which are basically at very high Coulomb number also, right. So, that we have seen some examples, okay. So, why do these schemes behave in many different ways? We have schemes which are like the leapfrog scheme or Lax scheme, Lax scheme, and there are so many other schemes, okay, and you will have tough choice deciding which scheme you should use for your particular problem, right, unless you have the understanding of like what are the characters of the different schemes, what are the properties of these schemes, right. So, in today's class we will discuss about some properties of the scheme, and in the subsequent classes we will go in detail about these properties. So, one property that we have already discussed is the consistency of the scheme, right. What is consistency? That as your delta t goes to 0, your time step goes to 0 and delta x goes to 0, basically your finite difference equation becomes your PDE, right. This is the definition of consistency. That means your discretization scheme or the numerical scheme that you are using is basically consistent. Okay. It does not say anything about the accuracy, because you may be using a very high delta t and delta x, and if you get a solution it need not be very accurate, because it says nothing about your accuracy, but it only says that these are consistent, and your FD will go to PDE provided your time step and the spatial step goes to 0. Okay. That means your discretized problem is now going to a continuous problem. Okay. Next is the stability. Okay, we will look out about the stability, and we will give a more formal definition about the stability in the subsequent slide. But for now we know that some schemes are stable, that means that solution do not blow up, okay, with time, okay, and you get the solution. It may not be very accurate, okay, but you get a solution, it is not blowing up. Okay. So, how do we determine stability of a scheme a priori before using it in a problem? Of course, when you use a problem without thinking about the scheme, it is likely that the scheme will blow up, and then you have to go back and basically find out why it blew up, right. So, that is the thing that we are trying to find out, that whether the scheme is stable or not, and there is a formal definition to that. We will look into that later. Okay. Finally, the thing is third is convergence. Okay. So, convergence is also the term you might be using it very often in your CFD. So, it is basically you are trying to solve a problem on the computer, okay, and let us say you have an analytical solution available from your fluid mechanics, physics, or whatever thing you want, right. And if the difference between the two goes goes down, okay, with time, okay, that means the solution is converging. Okay. That means a more formal definition, as we will provide later, is as the delta t goes to 0 and delta x goes to 0, your numerical solution is basically equal to the exact solution of your mathematical model, okay, basically your PDE that you are trying to solve. Okay. So, that is convergence. Typically, you might be looking at the curves, for example, your continuity or momentum, x momentum, y momentum, and you would be looking at the number, let us say 10 to the power minus 5. Okay. You started from value, let us say 10 to the power 0, and then you went all the way to 10 to the power minus 5, right. So, then you say that okay, this is the acceptable level. So, your equation, let us say n u is equal to 0, okay, and your numerical solution is n is equal to 0. Okay. So, you want to see the difference between the two. So, this convergence is nothing but the difference between the two, nu minus nu n for different variables, okay, for different equations. Your continuity, this may be your continuity equation, momentum equation, or energy equation. So, this is the difference between the two, and you are looking at the difference between the two, okay, and when it basically goes to a certain level, you say that it is converged. Okay. Many times you do not know the analytical solution, right. So, there also you have certain measures to find out the convergence. For example, let us say that your change in a particular equation, or let us say you are trying to solve that my continuity equation, the mass conservation is maintained, right. So, del u by del t plus u del u by del x equal to 0, right. So, so that is what you want to maintain, right. So, if the value will start from a very big value from the initial condition, but ultimately it will go down, and let us say it went to a value which is around 10 to the power minus 10, then you can say that it is now basically acceptable value for us to consider the mass conservation is obtained, right. Finally, we will look into the accuracy, right. So, the accuracy, there are two kind of errors normally found in CFD calculation. One is termed the dissipation error, another is called the dispersion error. We have looked the dissipation errors a lot in when we said that okay, when you refine the grid, the solution becomes better. So, that means that there was some error which was coming due to the numerical diffusion. So, that kind of errors will be come in the dissipation error. So, let us say you had a profile, you started like this and you are convecting it. So, it should convect as it is, okay, it should go like this, okay, but what is you are getting is basically something like this, okay, as we have seen from our solutions. So, that means that some dissipation is happening, okay, despite you not putting any dissipation in the equation, right. So, that is the kind of dissipation error. Other is the dispersion error, okay. So, here I mean if you for example, look at the case where we use the FTCS, okay, and you would have seen that there were so many wiggles here, okay. So, the terms which are basically containing the odd derivative. So, if you have a leading truncation error which is basically of even derivative, okay, del to u by del x square or del for u by del x 4 and so on and so forth. These even derivatives typically give you the dissipation error. On the other hand, if your leading truncation error has got del q u by del x cube or del 5 u by del x 5 and so on and so forth, these terms basically gives you the dispersion error. And we will look into both these errors in more detail in the subsequent classes. Okay, so let us start with the these three properties now, okay, because they are very useful properties for a scheme, and then we look at the accuracy aspects. Okay, first we want to make sure that the scheme is stable and it is converging, then we will look at which scheme is more accurate. Okay. So, we just want to discuss one thing. Okay, this is consistency, stability. So, right now you have got a PDE, right, you start with a PDE, okay. The PDE can be del u by del t plus c del u by del x equal to 0, okay, this is your PDE. Then you apply a numerical scheme on this, okay. This can be for example or FTCS, okay, and when you apply a numerical scheme in this, you will get a FDE, okay, which is basically the finite differential equation, okay, and that will look like, for example, in this case this is u n plus 1 I minus u I n by delta t and plus c u I plus 1 n minus u I minus 1 n by 2 delta x is equal to 0, right. Now, from your PDE you can have a solution, okay. Let us say you call it a solution of the mathematical model or the theoretical solution, okay, or the analytical solution, okay. So, you have a solution which is, let us call it analytical solution, okay. When we solve this equation FDE, you will have a solution, okay. Let us call it as a numerical solution or the computed solution, okay. But in between you will have, because you are using a particular numerical scheme, so you will have the exact solution of the numerical scheme. What is that? Basically the solution of your modified partial differential equation, MPDE, right. So, let us call this the exact solution of the numerical scheme, okay, which is nothing but the solution of MPDE. Okay, this numerical solution is different from exact solution of the numerical scheme. So, this is your discretized equation, finite differential equation, or this is your numerical scheme, this is a PDE. Why? Because you can have the round off error, okay, in between you can have the round off error, right, because of the system precision, okay. Plus we also have left some of the, so we have, when we are talking about the MPDE, okay, we are basically ignoring some of the higher order terms, right, which are still present in your error. So, those errors can also pip in. You can also have some errors due to your initialization or the initial condition that you are putting. So, all these things you can ignore, okay. So, so all these things if you consider, then this the solution that you are getting is your numerical solution, okay. Now, the consistency as we have discussed is basically between your PDE and FDE, right. These two together they give you the consistency, right. So, consistency is a condition, the consistency is a condition on numerical scheme that says that as delta t goes to 0, delta x goes to 0, okay, your FD goes to PD, right. That is your consistency. Now, look at the stability criterion. Okay. So, the what stability says is basically you have the exact solution of the numerical scheme and you have the numerical solution, right. So, stability, so this is your stability. So, the stability criterion says the error between the numerical solution and the exact solution of your numerical scheme will remain bounded as time progresses, right. So, if you have, let us say I define the error which is epsilon s, is the stability error, okay. So, that means it will be basically if you have, let us say u y n, this is your the numerical solution that you are getting from your computer minus u I and n, and this is your, let us say exact solution of your MPDE, right. So, I will call it, let us say u I n bar, right. So, this error should not become infinitely big, okay, as the iteration progresses, okay. So, that means that as you go ahead in time, at any given time the error should not be unbounded, okay. It does not say that error may not become very large at a given point of time, okay. At a given time it may become very large and that may not be acceptable to you also, and then it can become low. So, you can define that, okay, epsilon s is basically has to be less than some factor, let us say call it beta, okay, at any given time, okay, where beta is a very large number, okay. So, the error between your numerical solution and the exact solution of a numerical scheme will remain bounded, and it has got nothing to do with PDE because PDE does not come into picture here in stability, okay. And the last thing is basically your convergence. So, convergence basically connects your numerical solution to your analytical solution, okay. This is your convergence, okay. So, what convergence says is that if delta t goes to 0 and delta x goes to 0, that means for very small time step and the spatial step, your numerical solution. So, if I write it as u I n and minus analytical solution, okay, let us call it u I a, okay, analytical solution, and that I call it epsilon c, which is the convergence. So, that goes to 0 as delta t goes to 0 and the delta x goes to 0. Basically, your numerical solution approaches the analytical solution when the you make the grid size and the time step size very small, right. So, that is what your convergence criteria says, okay. So, the consistently connects your finite difference scheme with your PDE, okay, and you know that finite difference scheme comes from your numerical scheme, and your numerical solution and the exact solution of the numerical scheme is connected by the stability, and the stability criterion says that it should remain bounded, the difference between the two should remain bounded at any given time. Okay. And the convergence basically connects your numerical solution to your analytical solution, and it says that if your delta t and delta x is very small, then your numerical solution will approach the analytical solution. Okay. Yeah. So, the difference between the two goes to 0 as your delta t and delta x goes to 0. Okay. So, I hope this diagram is clear to you. This is purely due to the mathematical model. Okay. This is due to the mathematical model or the PDE. This is due to the choice of your scheme. Okay. And this is the solution that you are getting out of your computer. Okay. Now, there is a very famous theorem called Lax equivalence theorem. Okay. And this is a very important theorem in CFD, and what this theorem says is basically for a well posed initial value problem, okay, and a consistent discretization scheme. That means, we have already talked about the consistency here. Okay. The stability is the necessary and sufficient condition for convergence. That means, for a well posed initial value problem, if your scheme guarantees consistency, okay, and if it is stable, okay, if your scheme is consistent and if it is stable, okay, stable in the sense that we have derived that the difference between the numerical solution and the exact solution of your numerical scheme is remains constant, it does not go unbounded, then these two basically these are the necessary and sufficient condition for convergence. Okay. So, you are guaranteed to get the convergence if you have a consistent and stable scheme. Okay. Now, consistency we have already seen how to find it out. Okay. Basically, you take your FD, basically the finite differential equation, put the Taylor series and see that as the delta t goes to 0 and delta x goes to 0, is my truncation error going to 0 or not. If the truncation error is going to 0, that means your scheme is consistent, and most of the scheme that we have talked about in our lectures earlier, whether it is FTCS, FDBS, your implicit schemes and all those schemes, you can go back and do the Taylor series analysis, and you would see that your truncation error goes to 0, because the very fact that we have used the Taylor series for those derivations, okay, we are ignoring the higher terms which consist of this delta t and delta x. So, most of the schemes that we have talked are basically the consistent scheme, but we have seen that some schemes are not stable. For example, FTCS is not stable for convection. Okay. Also, FTBS is only stable for convection if C delta t by del x is less than 1. FTCS is stable for diffusion if nu delta t by del x square is less than 0.5. So, these are our observations, right. In the next class, we will go formal analysis of stability of a numerical scheme, and that analysis is called the von Neumann stability analysis. Okay. There are many ways to basically analyze. There are matrix approach, okay, and there are some more approaches, okay, but this is the most popular approach, analysis, okay, that we will be doing in the next class. Okay. And this will give you us a lot of information. Okay. Although I must tell you at this point of time that all these stability analysis that we have, okay, that we will be discussing in the next few classes are only done for the linear schemes. Okay. So, you might be disappointed that our non-Navier-Stokes equation that we are trying to solve is a nonlinear problem, right. So, how do we basically use these whatever results that we are getting from the stability analysis. So, you will be, I mean, despite of the fact that we are using for the linear scheme, the observation that we get is actually quite useful for a nonlinear problem also. Unfortunately, we do not have an analysis approach that can work on a nonlinear problem, because it becomes quickly very complicated and it is very difficult to perform that analysis. Okay. The other thing that particularly with the Neumann stability analysis is that it assumes here that your problem is periodic. Okay. So, for example, let us say if I have a problem where you say that u x is equal to some f x, okay, or let us take a simple example, okay, f x is equal to x square between 0 to x to 5, okay, then f x plus 5 is equal to f x. Okay. So, this condition is called the periodic condition. That means your signal is repeating. Okay. So, if your signal is something like this, okay, and then you say that okay, f x plus 5. So, this is between 0 to 5, okay, it will repeat like this for next 0 to 5 and so on and so forth. Okay. So, it will be basically periodic, right. So, for example, the sin x is periodic in 2 pi, right. So, this one Neumann stability analysis is basically for a class of problem, linear problems where your problem is periodic. Okay. So, why you need a periodic condition? Because this analysis is based on Fourier and such. Okay. So, you basically try to represent our function in Fourier series, okay, and you know that for a representation in Fourier series you need to have a periodic domain, right, and then only you can apply the Fourier series. So, that is another limitation of this analysis, that it is done for a periodic domain, but then again also it works quite well. I mean the basically insights, I will not say that the exact results that we are getting, but the insights that we are getting from this analysis are quite useful in practical problems also. Okay. So, we will start looking at the stability criteria characteristic of many different schemes in the next couple of classes, and as we know that when we ensure that the scheme is consistent and scheme is stable, that gives you a lot of basically confidence that your scheme is now going to converge. The only thing that will be remaining after that is that the converged solution that you are getting, how accurate it is, right. So, that also is another aspect where we have to see the error due to the computation, and we will look into that after we have seen the stability and the consistency. Thank you very much. Okay, we will meet in the next class.